Hello, good morrow. So today we're going to go through chapter 1. This should be fairly familiar because we went through it last week. If you have questions, you guys know what my office hours are. To start off, these vocab words should be done at home. They're in your book. We've also gone over the parent functions during last class, the 4 types that we're going to be looking at: the constant, linear, absolute value, and quadratic. On the next page, we've already gone through 1, 3, 4. We skipped number 2, 5, and 7. What we haven't gone over is this page. So I've written some things in here for you guys. So for number 8, we're going to start off with writing our table. And I've already chosen some numbers. But this is supposed to be positive too. My bad. So I've started with my table for number 8 with -2, 0, and 2. And now I'm just going to go ahead and plug those in. So we're going to have H. And oops, sorry, sometimes my iPad will go a little crazy because it is ancient. So H, I'm going to start with -2. -2 squared. -2 squared is 4, so that's 4 equals -4. So I'm going to go ahead and plug that in here, -4. Oops. The next thing that we're going to put in is a 0. That's the next up on our table. So h of 0, oops, that gives us 0 squared is 0 times a negative, it's still 0. Okay. Then we're going to go ahead and do number 4, or sorry, number 2. So we're going to choose 2. 2 squared is 4 times a negative is -4. That's going to be put in there. Next, we're going to go ahead and graph everything. I'm going to start with the furthest left, which is -2, -4. So we go over -2, and we go down -4. The next thing I'm going to choose is 0, 0. And then I'm going to choose 2, -4. And then from there, we're just going to connect our lines. We're going to try our best to make them nice and round. And that's it. The next thing that we're going to talk about is number 9, is 1/8 x squared. Okay. Oh, and if I'm not mistaken, I think we have to name the parent function and describe the transformation. So the transformation for this one, because we're not graphing the parent functions, we're just looking at them, is I'm going to say that this is a reflection across the x-axis. So reflect, across x-axis. And again, I'm sorry about my spelling, but it should be okay. Next thing we're going to do is number 9. So we're going to choose -8. Because that's what I did for my table. I chose -8, 0, and 8. And that's going to be 1/8 times -8 squared. Okay. So first we have to deal with that exponent, and 8 times 8 is 64. So that's going to be 1/8 times 64. And then we have to ask ourselves, well, what is 64 divided by 8? It should just be 8. The next thing that we're going to do is we're going to, oops, wrong 8, is we're going to plug in 0. We should have 0. 0 squared is 0 times 1/8 is still 0. Love it. Then the last one for this one that we're going to do is +8. 8 squared we said was 64, divided by 8 is 8. Okay. And this one, again, the parent function for this one is still going to be a quadratic, or an x squared, right? So I'm going to plot my points. I'm going to start at -8, 8. Oops. I did not want to plot. There we go. 0, 0. And 8, 8. Okay. We're going to make that as wide and round as possible. trying not to make it pointy at the bottom. It's very hard when my iPad only wants to make pointy lines. There we go. Okay, so this one, I'm going to go ahead and say that this might have been a stretch. Okay, and we're going to talk about the different types of stretches in the future, but I'm going to say that this one is probably actually, I'm going to say vertical shrink, and we'll see why in just a minute. Okay, and if you are so curious, let me see what page that's on, because we haven't quite gotten there yet, but we're going to figure that out when we get all the way over to page 9. Page 9 and 10. Oh, and 11, now that I'm looking at it, and 11. Love it. Okay. All right, this next one, you can go ahead and graph this one in Desmos. This is one of those occasions where we can use Desmos. I've also sketched the graph over here, just in case. And I've put the parent function in blue, and I've put our transformed function in red. The family is the absolute value function, yeah? When we're looking at all of our possible x values, which is the domain, I notice that if I come in from the left side, I can hit every possible value coming in from the left for my x's, like there's no discontinuity. And then the same thing coming in from the right, I can have every value on the right side as well. So we're going to say that's all real numbers. So I can choose any x value starting at -infinity to +infinity. I'm using something called interval notation. So I'm going to go ahead and use these like fancy little brackets here in these parentheses. We only use parentheses with things that are exclusive and brackets for things that are inclusive, and we'll talk more on that later. My range is very similar. I notice that I can't choose any value coming from -infinity, right? That can't happen because there's nothing down there. But I notice that I do hit a point starting at 0, 0, right? And then I go all the way up forever and ever and ever towards +infinity, right? For that, we include 0 because we're starting at 0, and then we can go to +infinity. Okay. This next question says, the table shows the distance a biker rides on his first team relay competition. So we have a nice little table here. And it says for part A, what type of function can use to model the data? And you can see that I've already added some information in here. I've noticed that my x values increase by 1 each time, and so do they keep going, or English, oh my goodness, they'll keep adding 1 as we keep going. For our distance, which is represented by y, I notice that there's an increase of 12 each hour that he's there. So because we have equal increasing and decreasing, I'm going to go ahead and say that that's going to have to be our linear function. So I'm going to say linear function. Linear function. Okay. And there is a really good way to explain this linear function here. And that's going to be that it increases, the distance increases by the same amount of each interval. So input increases the distance. We'll put distance. Distance increases the same amount over each interval. Oops. Across each 1 hour interval. There we go. Okay. If a biker's teammate rides at the same pace but leaves 1 hour later, what type of transformation would this represent? This one's going to be a translation 1 unit to the right because we're shifting all of our time 1 hour later, right? So this is going to be translation 1 unit to the right. And for all of my visual people out there, if I have my number line and it starts at 0, 1, 2, 3, 4, and so on, if I started here at 0, I can keep going forever and ever, right? But if I shift 1 hour later, see how I've had to shift my original point 1 unit to the right. All right, so we're going to start with this one. We're going to go 2 units to the left, right? So this is going to be my rule, right? I'm going to choose 2 units to the left, which is going to be f of x plus 2. Yeah. So this is going to be g of x equals, because we've made a new function. This f of x is not part of this function. This f of x is part of the rule sheet that I'm giving you, so please don't get that confused. So I'm going to say g of x is 1/3 x plus 2, because I'm only manipulating the inside of the function. So I'm only manipulating where that x is. Okay. The next one that we're going to do is 6 units down, so that would look like this. Okay, which becomes f of x minus 6. So that means we're going to take the entire function and subtract 6. So this is going to be g of x is equal to negative x plus 9 minus 1 minus 6. I should make that more of a parenthesis here. So then if I go ahead and simplify, I will get g of x is equal to negative x plus 9, and then negative 1 minus 6 is negative 7. Okay. I'm going to go ahead and box my final answers here. Okay. This next one we're also going down, so this would also look like f of x minus k, k being a constant, and that constant is 7, yeah? So that would be f of x minus 7. So this is going to become g of x. We've named a new function. Frank's become Gary. And then we have negative 2x plus 2 minus 7. And that's going to go ahead and be g of x equals negative 2x. $2 minus $7 is negative 5. Okay, and that's my final answer. Let's move on to the next one. This next one, I'm going to go ahead and write the rule here, is that we're going to be talking about reflections across the x-axis. So that is going to look like negative f of x. Okay, so this one is going to become g of x equals negative 1/2 x plus 8, right? Because remember, my f of x is this whole thing here, right? And I'm just multiplying it by a negative. And that is going to become g of x equals, using the distributive property, negative 1/2 x minus 8. Okay. The next thing that we're going to do is a reflection across the y-axis, and it's very similar to the reflection across the x-axis, but instead of having the negative on the outside of the function, we're going to apply that to every x value. Okay. So this one is going to become g of x equals 4 plus the absolute value of negative x, because I'm multiplying all my x's by a negative, plus 1. You can also think of it like you're substituting for every x you see, you're going to substitute it for a negative x. Okay, and that's just going to go ahead, we can drop those parentheses. It's just a habit of mine that I have to always use my parentheses, and we'll have negative x plus 1. Awesome. Let's talk about vertical shrinks. Vertical stretches and shrinks will be very familiar, or very similar, right? In that they both have the same rule. It just depends on whether or not we're using a fraction or we're using an integer. Okay, so a lot of times fractions, right, we'll sometimes see them written like this, right? And that just means a number between 1 and 0. So we're not negative, but we're also not a whole, like an integer, right? So we're going to be stuck between 1 and 0. So those are going to be numbers like 1/3, 1/2, 0.39, anything that's less than 1 but greater than 0, that's where we're going. Another way that we'll see this written is like this, and please don't mistake this for points. This is an interval. Okay. Our rule for this one for a vertical stretches and shrinks is a times f of x. Okay. When we are talking about a shrink, we're going to go ahead and we're going to choose the fraction. So this one is going to be a equals 1/5 because we're talking about a shrink here. So this is going to look like g of x equals 1/5 negative 5x, right? Because my a was 1/5. And then I'm just going to simplify. So g of x is equal to 5 divided by 5 is 1, so negative x. Okay. And that negative comes from negative 5 over 5, negative 1, and then we get negative 1 times x equals negative x. Okay. Alrighty. The next thing that we're going to do is a stretch. So this was a shrink and this was a stretch. So we are going to choose numbers that where x is greater than or equal to 1. Okay, so this is going to be the same thing, a times f of x, but this time because we're stretching, our a is going to be equal to 4. Okay. Oops. And though when we choose our a, that has to do with this factor bit, where it says a factor of 1/5 or a factor of 4. So this one is going to end up being g of x equals 4 times x plus 3 plus 2. And a common mistake that I see happening a lot, oops, 1 second. A common mistake that I see happening a lot is people treat the absolute value signs as parentheses. They are not. We're just going to leave them alone. And the reason that I didn't apply that to the 2 is because I really only care about where my, like, quote unquote parent function was. And that would be here. Yeah, it would be only in this part right here. So this is going to become g of x equals x plus 3. Or 4 for absolute value x plus 3 plus 2. Another one that we have here is horizontal stretch by a factor of 6. So this one's a little different. It says horizontal, right? And it also says by a factor of 6. Horizontal stretches and shrinks are not the same as vertical stretches or shrinks. We talked about rubber band theory in the class, or hair tie theory, whatever you want to call it. You'll notice that they look similar, but they are not the same. So what we're going to have to do is, since we're going by a factor of 6, right, well, first of all, our rule looks like this, but because we're stretching, I'm going to choose the reciprocal of 6, so b equals 1/6, okay? So we're just going to choose the fraction version of 6. So that's going to look like g of x equals, and I'm only going to apply that to my x's, so 3 times 1/6x minus 9, right? 3 over 6 simplifies to be 1/2. You could also think of it of 3 divides 6 2 times. So this would become g of x equals 1/2 x minus 9. Another one is a horizontal shrink by a factor of 4. So this one is going to be very similar. We're just going to choose the opposite, or the reciprocal. And the reciprocal of a fraction is its whole number. So we're going to choose b equals 4. Okay. For all my fraction friends out there, I do want to get very familiar with fractions. What that looks like mathematically is 1 over 1/4. That's 1 divided by 1/4. Then we keep, change, flip, or backwards KFC. 1 times 4, because you keep the first number, you change it to multiplication, and then you take the reciprocal, or you flip the fraction, and then we get 4. Okay. Or you can just think, flip 1/4, right? But I like this way because this red way is going to get us to a lot of different places in the future. So this one is going to be let's do g, because we're talking about a new function here. G of x is equal to, and then we are going to go with -8 times 4. Okay. Oops. Minus 4. Okay, and this should get us g of x was negative 32x minus 4. Consider the function f of x equals the absolute value of x. Write a function of g whose graph represents, we have our order here, a reflection in the x-axis. Then we're going to do a horizontal stretch by a factor of 3 and a translation of 5 units down. Okay. Awesome. So we're going to have g of x equals, the first thing we need to do is a reflection across the x-axis. And I'm actually going to write the order of my transformations over on the side here. So I'm going to have f of x, and then if we do a reflection, right, that's going to go ahead and give us a negative f of x. Then we're going to go ahead and do a horizontal stretch by a factor of 3. Okay. And then we're going to go ahead and translate 5 units down. So see how I'm just combining all of my rules here? That's what this is going to look like. Okay. So I'm going to start with g of x equals negative absolute value of x. That should be the first thing. Then I know that I have to do my horizontal stretch by a factor of 3, which means that my b is equal to 1/3. Yeah. So this is going to become 1/3 right attached to my x. And then I'm moving 5 units down. So I'm going to go ahead and then subtract 5 because we're going 5 units down. Okay. And that is my solution. That's it. And then we have, for our last question here, which of the transformations in section 1.2 will not change the y-intercept of this function? Okay, so we don't want to change the y-intercept. So let's go ahead and draw it. Give a little sketch here. This is my y, this is my x. We go 1, 2, 3, 4. I'm just going to graph it really quickly. You guys can graph it on your own time if you'd like. That's what it looks like. So if I move it up or down, right, if I do a vertical translation, that would not work. So I'm going to write my words out. Vertical translation. We have horizontals. And then our last one is we are going to have, we have 2 more. We have reflection in the y-axis, and then a reflection in the x-axis. Then we could also have a vertical stretch or shrink. Or a horizontal. Okay, so we can't do a vertical transformation because that's moving up and down, and that would change this point, this 0, 3 that we want to keep. Okay, so that would not work. So we can go ahead and cross that one out. And I'm actually going to do this in a different color here. So I'm going to cross that one out. Okay, a horizontal translation would also change it because that means that we move this way, and then if we move that way, this point would end up becoming the y-intercept. So that wouldn't work either, right? Even if I move towards the left, I would have some point that's not 0, 3 on the original graph become the new y-intercept. So that one would also not work. A reflection across the y-axis would work, right? Because if I move it around this axis, that is totally okay. However, if I move it around this axis, you'll notice that it will end up down here. And that's not okay. So we're going to go ahead and erase that one. Vertical stretch or shrink. I'll let you guys know right now that vertical stretches or shrinks, the x-intercept would stay the same. So this one's not going to work. So x-intercept stays the same. So that one's not going to work. But for a horizontal stretch or shrink, the y-intercept will always stay the same. Okay, so those are our two answers, is that we could have the reflection in the y-axis or the horizontal stretch or shrink.